Welcome to the Deep Dive. Today, we're not just looking at the future of transportation. We're breaking down one of the most technologically intense engineering challenges in the world, the stack that powers autonomous vehicles.
It truly is. It's really a mashup of so many different fields. I mean, building an AV isn't just about software and mechanical engineering.
Right.
You're pulling in AI, deep learning, these really sophisticated sensor arrays, embedded real-time operating systems, advanced networking. The sheer complexity of that stack is just, well, it's staggering.
And our deep dive today focuses on this revolutionary theme that's making this incredibly complex field more accessible and really speeding up its development. Yeah. The power of open source software and tools.
Exactly.
Our source material lays out this fascinating roadmap showing how open source is, lowering costs, democratizing research, and really shaping everything from how a sensor processes data to high-level cybersecurity.
The ability to share algorithms, to share frameworks and data sets is frankly the only way this field could have progressed as quickly as it has. Historically, the kind of data and the computing power you needed, that was all locked up in proprietary budgets that only, the giants could afford. Open source just bypasses that entire barrier.
So today we're going to cover the whole spectrum. We're talking about the 4 essential sensor types, the critical algorithms for localization and mapping.
All the way up to these advanced cyber war gaming platforms that are designed to test a vehicle's security. It's a huge topic.
Okay, let's unpack this with a surprising observation right off the bat.
Yeah.
One that I think perfectly illustrates this whole philosophy of sharing blueprints.
Oh, this is a great place to start.
When we talk open source in the car world, we're usually just thinking about code, right? But this philosophy, it extends to the actual physical car itself.
Yeah, that's the OS vehicle tabby. It's such a fantastic example because it grounds the whole concept in something physical. This wasn't just a design on a screen. It was a real functional open source platform.
Meaning the blueprints, the actual CAD files for the chassis, the engine mounts, the suspension, the brakes, all of that was publicly available.
All of it, under a Creative Commons license, so anyone could use them.
Imagine logging onto a website and literally downloading a car. The whole idea was to empower anyone, right? From a high school tech lab to a major car company to build their own custom electric vehicle. They basically democratized the hardware.
And the design itself was all about simplicity and accessibility. I mean, the basic chassis for the Cabby, it was so modular that 2 people could assemble it in under 45 minutes.
Wow.
It was designed for 2 to 4 passengers, so it was a functional, basic platform you could then build on and test your AV components.
And crucially, the cost reflected that democratization. I think the source said back in 2014, the base platform was only about 2,000 or 3,000 euros.
Yeah, around 1,990 euro for a 2-seater. That price for ready-to-assemble car frame, it just perfectly demonstrates the core idea. Get rid of the cost barriers to speed up experimentation.
Whether it's code or sheet metal, it's about letting others build on what you started.
Precisely.
Now that we've established that foundation, let's get into how the vehicle actually sees the world. This perception, it isn't handled by one single, all-powerful sensor. It's a really sophisticated, redundant mix of 4 distinct sensor types.
Right. Each one is designed to cover for the other's weaknesses. This is the essential sensor quartet.
The engineering challenge here is all about safety, isn't it? Making sure no single weather condition, for instance, can completely blind the vehicle.
It is. And every sensor involves a fundamental trade-off. It's usually resolution and accuracy versus cost and, how well it performs in the real world.
Okay, so let's start with the sensor that gives arguably the most detailed map of the world. LiDAR, light detection and ranging. This is the one we always see, that skinning dome on top of the test cars.
That's the one. LiDAR works by sending out laser pulses and then measuring the time of flight, or TOF, to calculate distance. And what you get back is this incredibly dense, high-resolution 3D point cloud.
How accurate are we talking?
We're talking centimeter-level accuracy, often. It allows for really precise measurements of an object's distance and its shape, which is critical for telling objects apart. And it's a long-range sensor, too, often seeing out past 250 meters.
I saw an image in our source material of a Velodyne LiDAR point cloud, and if you see it visualized, it's like a perfect digital ghost of the world. Every tree, every curb, every person is just outlined in millions of little dots.
And that visual precision, it comes at a cost, both literally and figuratively.
Literally, it's expensive.
Oh yeah, cost is the first big hurdle. A typical LiDAR unit is still pretty expensive, somewhere between $4,000 and $10,000 usually, though solid-state LiDAR is supposed to bring that down.
But the bigger issue is performance, right?
Yes, more critically, LiDAR's performance just falls off a cliff in harsh weather. Fog, heavy rain, snow. All of that causes the laser light to scatter.
So the data it gets back is just noisy and unreliable.
Exactly. It significantly reduces the range, and you just can't trust what you're seeing.
Which is why the AV needs a completely different way of sensing to back it up. Enter the incredibly reliable radar.
Radar is the pragmatic workhorse of the sensor suite. It also uses time of flight, but it's sending out radio waves.
And radio waves don't care about rain?
Not at all. Radio waves slice right through all the environmental problems that stop light-based sensors dead. Rain, fog, bright sunlight, snow, dust. Radar performance is barely affected.
Plus, it's way cheaper than LiDAR. That's why we're seeing it in a lot more consumer cars for things like adaptive cruise control.
Exactly. And it has this unique property called the transvision effect.
What's that?
Well, because radio waves reflect differently than light, radar can sometimes pick up reflections that bounce off, say, a wall or a large truck, so it can give the car a sense of traffic or an object that's just around a blind corner.
So it can literally see through things, in a way.
In a way, yeah. But this robustness has its own big weakness: interference.
Right. And interference is a huge problem that only gets worse as more of these cars get on the road. Why is that?
Well, the radio wave interference can come from the sensor itself, from other radar units on the same car, or in heavy traffic.
From every other car on the highway.
Exactly. Imagine a dense urban highway. It could become just saturated with conflicting radio signals. And that interference increases noise, it degrades the quality of the measurements, and it could potentially limit how reliable radar is when you're in bumper-to-bumper traffic.
Okay, so next up, we have the most common sensor of all, the humble camera. This gives you the context that the other sensors are missing.
Cameras are absolutely essential because they capture RGB data color, texture, visual detail. This is how an AV reads a street sign or tells the difference between a green light and a red one. And of course, they're incredibly cheap and widely available.
But cameras have the same Achilles heel as LiDAR, maybe even worse.
For sure. They are the sensor that is most inhibited by bad weather, and especially low light. Fog, rain, glare from a wet road at night.
A human driver can sort of squint and figure it out. A computer struggles.
Deep learning models really struggle with obscured visual inputs. Now, there are ways to mitigate this, like using thermographic cameras to detect infrared light in low-light conditions, but nothing really replaces that high-res visual input for understanding a scene.
And finally, the short-range specialist. Ultrasonic sensors.
These just use sound waves and time of flight. They are the cheapest sensors of all, and they are the most accurate for very close-range maneuvers.
They're what we already use for parking sensors.
Right, so they're proven technology.
And they work just fine in rain and snow. They're absolutely essential for low-speed tasks, like navigating a tight parking garage where you need that centimeter-level accuracy right next to the car.
So we have this quartet. LiDAR for the high-res 3D map, radar for speed and weather resilience, cameras for the visual context, and ultrasonic for close-up precision. But the real magic isn't just collecting the data, it's merging it all together.
That is the critical point that often gets overlooked. The car isn't looking at 4 separate feeds. It has to perform what's called sensor fusion. For instance, a camera sees a red object, and the radar detects an object at 50 meters moving at 10 miles per hour. Fusion is figuring out if that's a stop sign or a red truck.
Exactly. You have to align the light-based data and the radio-based data in time and in 3D space, and you have to compensate for the weaknesses of each one to create a single reliable picture of the world. If that fusion pipeline fails, the vehicle gets conflicting information and safety is compromised.
Once that fused data stream is established, the vehicle needs to answer the 2 most basic questions. Where am I? And what does the world around me look like right now? And that is the job of SLAM.
Right. SLAM simultaneous localization and mapping, it's the foundational spatial awareness component.
It's a continuous loop, isn't it? The vehicle has to build a digital model of its environment, that's the mapping part, while also figuring out its own precise position within that model. That's localization.
Precisely. And this is way more sophisticated than just GPS. I mean, GPS has accuracy limits, and it often fails completely in tunnels or between tall buildings in a city.
So this precise localization is what allows the car to plan a path or swerve to avoid something, right? What happens if that localization part fails?
If the localization drifts, even by a little, the vehicle might think it's in the center of the lane when it's actually 3 feet off to the side heading for a curb or another car. So yeah, SLAM is absolutely central to path planning.
And the algorithms for this, they're typically grouped by which sensor they rely on most.
That's right. You have a few main modalities. You can have classical algorithms, which are based on filters and math, or increasingly deep learning methods.
So let's look at those. Visual SLAM tries to do it all just with cameras to keep the cost down.
Visual SLAM is really attractive for cost, but it has some classic problems. The most famous one is scale ambiguity.
Scale ambiguity.
It's hard for the algorithm to accurately tell if an object is small and close, or if it's large and far away just from a single camera feed. Motion blur and big changes in lighting also cause a lot of instability.
And that's often fixed by pairing it with an IMU, an inertial measurement unit, which gives you visual inertial SLAM.
Yes, the IMU provides continuous measurements of acceleration and rotation. Now, it's not super accurate over long periods, but for short-term measurements, it's excellent at fighting that drift.
So it helps correct for motion blur and just generally makes the location more stable.
Dramatically so. And there are great open source frameworks like OrbiSlam and OpenSSFM that give researchers a really strong starting point here.
Then you have the high-performance benchmark, LiDAR SLAM.
Given LiDAR's incredible resolution, it's really the gold standard for mapping large, detailed areas. And the whole field owes a huge debt to the open source community here. The LOAM algorithm, that's LiDAR odometry and mapping, was a foundational breakthrough.
It was famous for how well it performed on the Kitty dataset, right?
Exactly. And because LOAM was shared openly, the community could just immediately start building on top of it.
So you get all these variations like FastLum and LegoLum that are all just refining that original idea.
Precisely. It's this collective open improvement process that lets AV development accelerate so quickly, nobody has to reinvent the wheel for core mapping.
Now, we mentioned radar SLAM is less explored.
Yeah.
Given how good radar is in bad weather, why isn't it a primary choice for SLAM?
It's fundamentally just a harder problem. Radar data is much sparser, it's noisier than a LiDAR point cloud, you get great distance information, but the angular resolution and the feature detail are often too low to build a really reliable, dense 3D map using the classic methods.
But the promise is still there.
Oh, absolutely. For a level 4 vehicle that has to operate reliably in a blizzard where LiDAR is useless, a robust radar SLAM solution is essential. It's an extremely active area of research, especially with deep learning.
Which brings us directly to deep learning SLAM.
Deep learning is definitely the future of this domain. AI models are being used to do the whole SLAM process end-to-end, or maybe more effectively right now, to just enhance the classical pipelines. They're just so good at processing noisy or imperfect sensor data and optimizing sensor fusion.
And underpinning all of this open source progress is the mandatory sharing of data.
You have to have it. Without shared, standardized data sets, researchers can't benchmark their work or compare performance. The KTI dataset was crucial for that, but now we're seeing these massive industry-backed datasets like Argoverse, Lyft L5, and the Waymo Open dataset.
So any new algorithm, which is often built with open source code, can be tested against the same complex real-world scenarios.
Exactly. It guarantees continuous, rapid improvement across the entire field.
So we have the eyes and the brain working together, collecting and processing all this real-time spatial data. But to train the deep learning models that make the actual decisions, when to brake, when to accelerate, when to change lanes, you need data that goes way beyond what you can safely collect on public roads.
That is the bottleneck. For robust motion planning and decision-making, these AV machine learning models require an absolutely immense scale of data.
We're talking billions of miles, right?
Billions! You simply cannot accumulate that kind of mileage safely or ethically in the real world. As Waymo has shown, hitting 10 billion simulated miles seems to be the necessary threshold for a really robust deployment.
And the cost benefit of simulation versus real-world testing is just overwhelming. I mean, simulation is faster, it's orders of magnitude cheaper, and it completely removes the danger and liability.
But it's not just about racking up easy miles on a virtual highway. Simulation is the only way you can do comprehensive robustness testing. You have to subject the software to thousands of these rare, unexpected, or dangerous edge cases that you might only see once in a million miles of real driving.
Like testing how it handles 9 different levels of fog, or simulating a multi-car pileup that requires a very specific defensive move.
Exactly. Simulators use these powerful game engines like Unreal Engine and Unity to generate synthetic data with high-fidelity graphics and realistic physics. This lets the models train on all sorts of complex variables. Different weather, different lighting, road damage, and interactions with all sorts of different agents, aggressive drivers, distracted pedestrians, motorcycles.
The quality of that synthetic data has to be so good that the AI can't even tell it's not real.
It has to be. And again, open source has really democratized this incredibly expensive and critical training phase.
So let's dive into the tool chest, starting with CarLA, which seems to be the industry benchmark for realistic simulation right now.
CarLA is built on Unreal Engine, and it has fantastic visual fidelity. It offers a really comprehensive suite of sensor models: radar, LiDAR, RGB cameras, and even these sophisticated ground truth sensors.
What's a ground truth sensor?
It's a sensor that tells the AI exactly what's in the scene with perfect accuracy. For example, semantic segmentation labels every single pixel as road, car, or tree. It's like giving the AI the answer key while it's learning.
And the configurability is huge. You can adjust 9 different weather conditions, change the fog density, the amount of rain.
Yeah, and shift the lighting between midday and sunset. The limitation, though, is a practical one. It's rooted in its asset library. CarLA has a relatively small set of pre-made maps and vehicle assets.
So the deep learning model runs a huge risk of overfitting.
Exactly. The AI learns to drive perfectly in that one specific simulated city, but then it fails immediately when it's confronted with a real-world environment it's never seen before.
So to enhance that variety, you mentioned Summit, which builds right on top of CarLA.
Right. Summit directly addresses that overfitting risk by focusing heavily on the diversity of agent behavior. It shares CarLA's core environment, but it introduces vastly more adjustable agent behaviors. You can set the aggression level of individual drivers, their attentiveness.
And you can add more types of vehicles, like motorcycles and buses.
Yes, and crucially, it can generate simulations from real-world map data using OpenStreetMap, which gives it much more map flexibility.
Moving to the other big game engine, we have the SVL simulator from LG, which runs on Unity.
SVL is known for its high degree of scenario configurability. They allow really fine-tuning of environmental factors, but they also allow for the simulation of road damage, which is a highly relevant real-world problem for these systems.
And it uses a formal language called Scenics for defining scenarios.
It does, which makes testing complex rare events highly repeatable.
Now, the sheer volume of synthetic data required makes this next one really intriguing. PG Drive, which focuses on procedural generation.
PG Drive's whole design philosophy is an active solution to that overfitting problem. Instead of using pre-made static maps, it uses procedural generation. It builds an infinite number of unique road layouts on the fly, just stitching together elementary blocks like roundabouts, ramps, and intersections.
So they're essentially teaching the AI to drive in a constantly generating, almost Minecraft-like world. You're forcing it to generalize its decision-making rather than just memorizing a map.
Precisely. You're trying to stop the computer from cheating on its own homework. It forces the model to focus on the general rules of the road, not the specific geometry of one map.
What's the trade-off?
The trade-off is simplicity. PG Drive currently has sparser sensor options, mostly just an RGB camera and basic LiDAR, and it lacks the really sophisticated weather and lighting features you see in RLA or SVL. It's prioritizing topological variety over visual realism.
And finally, we should touch on the pure traffic simulators, like Zumo and Flow.
These aren't focused on what an individual car sees, but rather on how the whole system flows. SUMO is purely algorithmic. It represents roads as graphs to calculate optimal traffic flow. No graphics, no sensor data.
And Flow builds on that.
Flow builds on SUMO, but it's focused specifically on simulating mixed traffic cases. So the interaction between large groups of human-driven cars and autonomous vehicles. This is vital for city planners to figure out the best policies for deploying AV fleets.
That brings us from the virtual training ground to the foundational software running inside the car itself. All that sensing and path planning has to run on a stable, secure, and incredibly fast operating system.
Right. The heart of the AV is its embedded OS, and it must satisfy a unique, completely non-negotiable requirement. It has to be a real-time operating system, an RTOS.
So why is real-time so mandatory here? What happens if it's just a standard OS, like the one on my laptop?
A standard OS uses a buffer. It's designed for throughput, meaning it prioritizes fairness and efficiency. A non-critical task might occasionally delay a critical one for a fraction of a second.
And in a car, that's not okay.
An RTOS operates without that buffer. It guarantees that a critical task like hitting the brakes based on an immediate sensor input will execute within a predefined, extremely narrow time frame. milliseconds. It uses a prioritized scheduler to make sure that life-critical actions always run first, immediately.
So the infotainment system loading a new playlist can't delay the emergency brake.
Never. That tenth of a second delay is completely unacceptable.
And beyond speed, the OS has to play nice with the rest of the robotics world.
Yes, compatibility with ROS, the robot operating system, is essential. ROS is this huge open source set of tools and libraries that lets all the different software modules in the car talk to each other reliably. Almost every open source SLAM algorithm or perception module is built using ROS packages.
Now, since failure can be catastrophic, there are formal security and safety standards. The sources really emphasize ISO 26262.
This is a cornerstone of automotive safety. It defines 4 automotive safety integrity levels, or ASIL, from A to D. And ASIL D is the highest level. It's applied to systems where a failure carries the greatest risk of severe harm or death.
And getting ASIL D certification isn't just about writing clean code, is it?
Oh, it's far more rigorous. ASIL D demands measures against both systematic failures, like flaws in the design, and random hardware failures. This means you need internal monitoring, hardware redundancy, often 2 processors doing the same task and cross-checking each other, and a highly restrictive development process. It's the stamp of trust that separates a prototype from a road-ready system.
We also hear a lot about hypervisors in these systems. How do they help with security?
The hypervisor is critical for isolation. Think of the AV as having 2 separate computers in one box. One runs the life-critical driving stack, the RTOS, all ASIL D certified. The other runs the non-critical stuff, like Android Auto or your music streaming.
And the hypervisor acts like a virtual wall between them.
Exactly. It isolates the memory, the processing power, and the I/O for the critical control systems.
Right.
So if a hacker finds a vulnerability in your Spotify app, the hypervisor prevents that exploit from crossing over and accessing the core braking system.
When we compare the open source versus proprietary options for these core systems, we really see the limits of open source for the most critical functions.
That's right. The main open source contender is automotive-grade Linux, or AGL. It's a great platform. It covers infotainment, 80 suits components, and it's compatible with open source hypervisors. However,
it's not an RTOS, and it's not certified under ISO 26262.
Exactly. It's excellent for non-critical functions or for rapid prototyping, but you wouldn't use it for the life and death control layer.
And that safety gap is why the industry leaders all stick to proprietary systems for that core layer.
Yes. The highest safety layers are dominated by proprietary RTOSs like QNX Neutrino, WinDriver VxWorks, and Green Hills Integrity. They are all certified with ASIL D, meeting the real-time guarantee and the formal security requirements that AGL currently lacks.
Now let's extend the vehicle's awareness outside its own sensory bubble. The car can only see so far, and that limit is broken by V2X communication.
Right, V2X, or vehicle to everything. This is the networking backbone that shares traffic and safety data between vehicles, infrastructure, pedestrians, and the cloud. It moves the car from being an isolated system to being a node in a network.
So let's run through the different classes of V2X, starting with peer-to-peer.
You have V2V, vehicle to vehicle, which is direct sharing of real-time data like sensor readings and safety alerts. This enables cooperative perception, where cars can share blind spot info or even collaboratively build a map of their shared environment.
And then V2P for safety.
Vehicle to pedestrian, which is critical for safety. It relays the location data of vulnerable road users like cyclists and pedestrians so the car can plan to avoid them.
And then you move up to the infrastructure layer.
Right, V2I, vehicle to infrastructure, connects the car to things like traffic lights and roadside units. This lets the car know a light is about to change or a lane is closed up ahead. And then V2N, vehicle to network, connects to the cloud for large-scale optimization.
The potential safety impact of this is huge. The NHTSA reports that V2X could prevent up to 500,000 crashes a year in the U.S. alone.
It's the power of the network effect applied to safety. And V2X is quickly expanding into the IOV, the Internet of Vehicles, which fully integrates cloud services and AI into this ecosystem. This is what enables things like remote chauffeuring or complex AR and VR infotainment.
And to make all this happen, we have 2 main network interfaces. First, there's DSRC.
Dedicated short-range communication. It uses limited-range radio waves up to about 1,000 meters, mainly for VRAV and V2I. It's valued for its low latency and its adherence to security standards.
And the alternative, using the cell network, is CV2X.
Cellular V2X, which leverages LTE and now 5G networks. It's more flexible. It has 2 modes. The PC5 interface is direct V2V communication, short range, low latency, and it works even if you're out of cell coverage.
So that's for immediate safety alerts.
Exactly. And then the UU interface uses the standard cellular network through a server. It has higher latency, but it's better for larger scale traffic coordination or streaming services.
Now, the networking brings its own security challenges, especially in dense areas.
Oh, yeah. One of the biggest threats to DSRC networks is something called a broadcast storm.
A broadcast storm.
Imagine every car in a crowded intersection trying to shout its location, speed, and direction all at the same time. The radio channel just gets saturated, data packets collide, and the safety-critical information gets slowed down or lost completely. It threatens the entire safety mission of DSRC.
Okay, before we compare the leading open source driving platforms, we need to be clear about what level of autonomy we're even talking about, using the standardized SAE levels of automation.
This classification is so important for understanding what the car can do, and more importantly, what the driver is responsible for.
So level 1 is simple driver assistance, like cruise control. Level 2 is partial automation. It handles steering and speed, but the driver has to be ready to take over immediately.
Level 3 is the big pivot point. Conditional automation. The system does the entire driving task when it's engaged, but, and this is the key distinction, the system can and will ask the driver to take over.
So the driver has to be ready to transition from just monitoring to actively driving.
Exactly. Then level 4 is high automation. The system controls everything and handles its own failures, so no human is required as a fallback. But it's usually limited to a specific area, like a geofenced robotaxi service in a city.
And level 5 is the ultimate goal. Full, unconditional autonomy. Anywhere, anytime, any condition. The unicorn we're all still chasing.
Right.
So with that in mind, let's compare the two major philosophies in open source ADS, starting with the very structured modular approach of Autoware.
Autoware, which came out of Japan, represents the traditional rigorous robotics approach. It's modular, it's built on Linux and ROS, and its specific focus is on autonomous driving in complex urban areas.
And that modular architecture means it breaks the driving task into these separate, manageable blocks.
Exactly. It segments the whole process into sensing, computing, and actuation. Sensing uses all the sensors we talked about. Computing handles the decision-making, localization, perception, path planning.
And the final layer, actuation, is what actually turns the wheel and presses the pedals.
That's where it uses these precise, rule-based control algorithms to follow the planned path. Autoware is a robust, full-stack, complex system, and it's been adopted by giants like Toyota for their ePalette and Foxconn for their big commercial platform. It's designed for guaranteed, predictable behavior.
Now let's contrast that very modular, rule-based system with OpenPilot from Comma.ai.
Yeah.
Their philosophy could not be more different.
OpenPilot is a radical departure. It's open source, level 2, semi-automated software, usually an aftermarket retrofit. And instead of breaking the task into dozens of separate modules, it uses a system-level, end-to-end design.
This means the entire driving decision, the steering angle, the acceleration, it's all output directly by a single large neural network that's just looking at camera images.
That is the key architectural shift, and this network is trained on a massive aggregated data set of over 100 million miles of driving, all uploaded by its users. This data-driven, holistic approach, they believe, yields a more fluid, natural, human-like driving experience.
And the numbers are impressive for a community project. Over 325 supported car models, over 10,000 users. And I saw that Consumer Reports actually ranked it above Tesla's Autopilot and Cadillac Super Cruise back in 2020.
They did, specifically citing its superior driver engagement and ease of use. And the Cannonball Run record is set 43 hours with 98.4% autonomy coast to coast. It just demonstrates how effective this continuous data-driven learning model can be.
And its features really highlight that strength. The lane centering predicts the safest path, rather than just rigidly following painted lines.
Right, and its adaptive cruise control uses map data to proactively slow down for curves. And its safety features are really refined. The driver monitoring system is very active. If the driver is distracted for more than 6 seconds, it warns them and then safely decelerates the vehicle to a stop.
So we really have this philosophical trade-off. Autoware offers predictable safety through its modular traceable components, while OpenPilot offers rapid, fluid iteration powered by massive user data, which often results in superior real-world performance.
And the industry is still trying to figure out which model or what blend of the two is the right path forward in the long run.
While the open source community is providing all this innovation, the commercial giants are the ones driving the actual deployment. Traditional car makers are closing the skill gap through acquisitions.
Right, you have Ford acquiring Argo AI, GM acquiring Cruise Automation. But the really big milestones are being set by the tech giants who are, at their core, software and data companies.
Waymo.
Waymo is the recognized leader in testing metrics. Their 10 billion simulated miles plus 20 million real-world miles. And they've been operating self-driving services since 2018. That shows the scale you need for commercial deployment.
And in the huge Chinese market, Baidu's Apollo is the strongest commercial force.
Apollo is itself an open source platform, which makes it a powerful example of the open model succeeding commercially. It has over 150 partners, including Ford and Toyota, and the Chinese market is absolutely critical. It's expected to be 2/3 of the global AV market.
Okay, that brings us to the final and maybe most critical trade-off: cybersecurity. We've established that the AV is this complex, hyper-connected, real-time computer, and a cyber attack could easily turn a vehicle or an entire fleet into a weapon.
The stakes couldn't be higher. And this brings us right back to that fundamental software debate, the open versus closed security models.
It's a conflict between two deeply held security philosophies, right? And right now, the industry is heavily skewed toward proprietary systems. The sources say only about 23% of automotive applications use any open source components. The tendency is to rely on security through obscurity.
That's the theory behind the closed system. It's a proactive approach. The idea is if the code is secret, malicious actors have to work a lot harder to find vulnerabilities.
But the downside is, if a vulnerability exists, detection often takes longer because only a small internal team is looking at the code.
Right. A zero-day vulnerability might just sit there undiscovered until an attacker finds and exploits it. The open model suggests the complete opposite.
The open system is more exposed because the code is public, which gives attackers a roadmap. But it enables a much more powerful reactive security response.
Because you have this huge community of white hat security researchers and ethical hackers constantly analyzing the code. The theory is that detection and patching of vulnerabilities will be much, much quicker because you just have so many more eyes searching for problems.
And this whole calculation shifts as we scale up from single cars to massive connected fleets.
At fleet scale, keeping secrets becomes almost impossible. And when the consequence of a breach is a fleet-wide failure, the rapid detection offered by the many eyes of the open source model becomes arguably more important than the temporary obscurity of a proprietary system.
We saw an analogy for this outside of security with the Volkswagen emissions scandal.
That's a perfect example. That deception was only possible because the system was a black box. The fraudulent algorithm was only found through this lengthy external analysis. An open source model would likely have exposed that code to the academic community much more quickly.
Transparency aids auditing, and in safety-critical systems, auditing should be mandatory.
It should. And we're seeing some commercial leaders test hybrid approaches. Tesla made its vehicle control security software open source.
That was a huge move.
It was. They basically said, we're confident in our internal patching, but we need the reactive vigilance of the global security community to find what we missed. It's an acknowledgement that for systems this complex, relying only on your internal team for security validation might not be enough.
To truly secure these systems, though, you can't just wait for vulnerabilities to be found. You need proactive, hostile simulation tools. And this is where OpenAEV comes in.
OpenAEV is a highly specialized open source platform. It's the industry's first threat-informed adversarial exposure validation platform. Its whole purpose is to formalize and execute these cyber adversary simulation campaigns against an organization's digital assets.
So this is like organized cyber war gaming against your own infrastructure.
That's exactly what it is. The objective is to move organizations away from just generic vulnerability scanning to a proactive security stance by emulating real-life attack scenarios, often based on threat models like the UMIAD ATT&CK framework.
And what are the core parts of one of these simulation campaigns?
It starts with the scenario, which defines the threat and the overall plan using these specific scheduled events called injects. Then the simulation is a single execution of that scenario.
And an inject is the attack itself.
An inject is the action, yeah. It can be anything from executing a hostile payload on an endpoint like planting ransomware on a developer's machine, to assigning tasks to your human team, like forcing your incident response team to communicate a breach under extreme pressure.
So how does the security team measure if they succeeded or failed during one of these campaigns?
That's handled by expectations. These are the defined outcomes the security team wants to observe. Did the security tool prevent the payload? Did it generate a clear alert? How quickly and correctly did the human analyst respond? All of that feeds into the final scoring and reporting.
And the system needs to push these attacks out and then pull the data back in to see what happened.
That's done through injectors and collectors. The injectors deliver the hostile actions, and the collectors retrieve the inbound data from all your security tools, your EDR, your XDR platforms. The collector then maps all that raw data back to the defined expectations, so you get a structured, verifiable evaluation of both your tech and your team.
What's really fascinating here is that OpenAEV doesn't work in a vacuum.
Yep.
It's plugged into a wider threat intelligence ecosystem.
It connects to platforms like the open source OpenCTI. This lets an organization build their adversarial simulations based on the absolute latest and most relevant threat intelligence. So you're not just testing against generic threats, but against the specific attacks you're actually likely to face in the automotive sector.
It's the bridge that takes abstract threat intelligence and turns it into tangible, verifiable security validation.
That's it, exactly.
We've taken a deep, really extensive journey through the autonomous vehicle stack. And what just shines through is the profound democratizing force of open source at every single level.
It really does. From the foundational SLAM algorithms that all came from open projects like Loam, to the necessity of training simulators like CarLA, the open source movement makes AV development cheaper, more collaborative, and just inherently faster.
And we saw that the AV has to run on this ultra-reliable real-time operating system, adhering to the highest safety certification, ASIL-D. That safety then gets extended by V2X networking, which pushes the car's awareness beyond its line of sight.
Though it has to overcome those critical networking challenges, like the broadcast storm and dense traffic.
And we saw that core architectural friction point, the contrast between the highly modular, traditional approach of Autoware versus the simplified, data-driven, end-to-end machine learning model of OpenPilot, which is proving to be incredibly effective.
Ultimately, the safety of AVVs requires these unprecedented levels of security validation, and the industry is still split between the commercial preference for proprietary, security through obscurity systems, and the necessity of the reactive vigilance that you get from open security communities.
Tools like OpenAEV really represent the future there, providing a way to rigorously test defenses against realistic attack scenarios, whether the code underneath is open or closed.
For sure.
So what does all this open source innovation mean for the commercial reality? We've seen that global AV platform providers like Waymo and Baidu are accumulating these massive advantages in data and scale. If the market follows the path of the smartphone, where proprietary software becomes the dominant layer on top of OEM hardware, then the platform providers will control the roads.
But the continued success of projects like OpenPilot shows that a powerful, community-driven alternative is still very much alive.
Which raises an important question for you, the learner, to consider as you watch this industry evolve. If the dominant commercial players favor proprietary control software, how might the continued necessity of open-source ADAS platforms like OpenPilot, which rely on shared user data for rapid iteration, and the critical need for advanced open security validation tools like OpenAEV fundamentally change those power dynamics?
Could the need for transparency and security and the sheer acceleration you get from community data eventually force even the most closed providers to open up more of their code, or risk falling behind in the race for verifiable safety?